This is a neuron cell imaged with a standard wide-field fluorescence microscope. We can observe the cell body, dendrites and spines. And this is the same cell image with a confocal microscope, which clearly shows the 3D structure of the cell. But we can make this image sharper and smoother by using the Rescan confocal microscopy technology, or RCM. The RCM is a new type of confocal microscope. It combines point scanning with a camera as detector. The RCM has all the features of a regular confocal microscope, but offers some important extras. Smoother images. RCM has a 4 times better signal-to-noise ratio. Sharper images. RCM offers down to 170 nanometer lateral resolution, 140% better than any conventional confocal microscope. A lower price. RCM is a camera-based technique without complicated electronics. This makes the RCM very affordable. The architecture of a RCM system is very simple, as it is connected with microscope and camera via a standard C-mount adapter. It is actually a box coupled in between your microscope and camera. The optics inside the box reads the object under the microscope and writes the information on the camera chip. To realize this, the RCM combines a standard confocal microscope with an extra independent rescanning unit. So the scanner reads the object on the X and Y axis, and the rescanner writes the image to the camera sensor. Now let's follow the light path of the RCM confocal microscope. First, we examine the light coming from the laser scanning the object. This is the excitation light. Second, we follow the light emitted by the object. This is the emission light. The excitation light path. The excitation light from the laser is guided by the fiber into the RCM unit. From the tip of the fiber, the light is collimated by a lens and hits the first mirror. The collimated beam is reflected by the dichroic mirror. The mirrors of the scanner direct the beam to the scan lens. Because each mirror rotates on an independent axis, the laser light scans the surface of the sample. The light propagates through the microscope and excites the sample in a small spot. Because of the scanning motion of the light, the scanner reads the object. The sample is labeled with fluorescent molecules. Light hitting the sample excites these molecules, and immediately fluorescent light of a longer wavelength is emitted. This is where the emission light path starts. The emission light path. The emission light propagates through the microscope towards the output port. It passes the scan lens and hits the X and Y scanning mirrors and travels in the opposite direction of the excitation light towards the dichroic mirror. There, it arrives at the dichroic mirror, allowing only the emission light to pass through. Next, the emission light is focused on the pinhole. The pinhole takes care of sectioning like any other confocal microscope. So far, nothing special happened. The light path is the same as any other conventional confocal microscope. Traditionally, there would be a photomultiplier tube as a detector behind the pinhole. But the RCM adds a revolutionary optical detection system that improves resolution and sensitivity. After the pinhole, the emission light path goes on. The emission light is collimated again and hits the X and Y rescanning mirrors. The emission light is directed via the rescan scan lens to the camera chip. Here, the image of the object is written point by point in a scanning manner. The image of the emitted fluorescent light appears in the camera and can be stored in the computer. By controlling the sweep of the rescanning mirrors, the resolution can be improved in the following way. When the sweep of the scanner and rescanner are identical, the RCM is converted to a conventional confocal microscope with a diffraction-limited resolution of 240 nanometer. But when the sweep of the rescanner is doubled, the RCM is converted to a confocal microscope with improved lateral resolution. The result is a resolution of 170 nanometer. Now let's examine the way RCM improves the resolution. Here you see a schematic representation of the principle. On the left, the blue laser spot is scanning through the sample. On the right-hand side, the emission spot as it is written on the camera chip by the rescanner. Here the sweep of the scanner and rescanner are identical, and we obtain the standard diffraction-limited resolution. Now, watch what happens when we double the sweep of the rescanner. The size of the rescan image on the camera chip will double, but the size of the rescanning spot will not increase. However, due to motion blur, the final size of the rescanning spot will be 1.4 times larger. Because the size of the image is 2 times larger and the blurring function only 1.4 times larger, we will effectively end up with a sharper image. This effect becomes clear when we rescale the image to its standard size. Now we understand why the double sweep of the rescanner in RCM gives an improved resolution of 170 nanometer. We also analyzed larger sweeps and found that the double sweep improves their resolution best. This formula describes the relation between the length of the sweep and the image resolution. It clearly shows that the sweep larger than double does not improve the resolution. This is the invention behind the RCM. By using the RCM, the resolution of the fluorescent sample is upgraded to 170 nanometer, while a conventional confocal microscope resolves only 240 nanometer. The RCM principle is optics only, so there's no software post-processing needed to achieve the improved image resolution. If we combine this with a sensitive camera detector, the RCM has a 4 times higher signal-to-noise level. Concentrated light without closing the pinhole. In conclusion, RCM is a confocal microscope. RCM has high sensitivity. RCM has 170 nanometer resolution. RCM is optics only. RCM is affordable. RCM has a fully open system architecture. RCM is designed by scientists for scientists. Visit our website confocal.nl for more information or request a quote from info@confocal.nl. Confocal.nl is a spin-off company of the University of Amsterdam.